Last time, we talked about the diffusion equation in equilibrium, which means that the concentration does not change with time and without accumulation. Today, we talk about the case where there is accumulation. Accumulation can happen because the chemical precipitates out of solution. A simple example is rain falling out of a cloud, which of course decreases the concentration of water vapor because it has changed into water droplets. Another example is something that many of us did as children, making candy out of sugar water solution, where as the sugar crystallizes, the concentration of sugar in the water must go down. What changes if there is accumulation of rate A? That is, at every point in the fluid, the chemical is either being generated, meaning positive accumulation, or destroyed or precipitated, meaning negative accumulation, at some rate A. The main thing that changes is the conservation of mass statement. For the volume, V equals A times dx, we have three terms affecting the total mass in the volume. First, the term that is the accumulation, which is equal to little a times big A dx. This is the accumulation term that is either adding or removing the chemical everywhere in that volume. There is the flux F at x1, and lastly there is the flux F at x2. Now here is the unintuitive part. We are assuming that the chemical process is in equilibrium, so the total mass in V still stays the same. Hence, we get accumulation plus F of x1 is equal to F of x2. Now we proceed just like we did last time by replacing the flux terms with Fick's law. Little a times big A dx minus d dc of x1 dx must be equal to minus d dc of x2 dx times a, and I'll put the a that I left out right there. Now we can divide by a and dx just like we did in lecture 14. This gives us a minus d dc of x1 dx minus dc of x2 dx, all divided by dx. And that entire equation must be equal to 0. Again, taking the limit as dx goes to 0 of this entire quantity gives us a plus d squared c dx squared is equal to 0. This is called the equilibrium diffusion equation with accumulation. Note that this implies a new type of solution, generally not a line. If A is constant everywhere in the fluid, what curve C of x has a second derivative that is constant? A parabola. Think for a moment about what this means. This equation says that the parabola will be concave down if A is positive, and concave up if A is negative. This makes sense because the only way that total mass can stay constant when A is positive is if the chemical is being removed at the boundaries of the tank. That should mean that in equilibrium, the concentration is higher in the middle than it is near the edges. So if I drew this situation, and if I say that C at 0 is equal to 1, and C at 1 is also equal to 1, then I might get a parabola that looks like that. That's my terrible drawing of a parabola. What happens when A is not constant as a function of x? This can happen for any number of reasons. Maybe sunlight is heating part of the tank but not the rest of it. So there is a temperature gradient in the fluid causing more accumulation in hotter places. Then we have A here being a function of x. If, for instance, A is equal to k times x, then the solution would be cubic in x. You will look at an example of this in the homework. Lastly, what happens if A is allowed to depend on C of x rather than x? This might happen when the ability to accumulate a chemical is dependent on how much is already there, which is what we mean by a solution becoming saturated. Then we have a diffusion equation of the form where A is actually a function of C of x. And if that was equal to k times C of x, we would actually expect to get C double dot is equal to minus k over d times C. Hopefully you recognize this as a linear, constant coefficient, second-order differential equation that is exactly the same as the spring mass system we have seen before, where the independent variable is now x instead of t. You know the solution to this from mechanical systems. The solution of this differential equation will involve sine and cosine terms that depend on x, not t. You will do an example of this as well in the homework. So what should you remember from today? Remember that introducing accumulation, which is often the goal of a chemical engineer, will generally lead to solutions that are not straight lines, but oftentimes you have all the tools you need to solve the differential equation. Next time we are going to look at what happens when the system is not in equilibrium. Even though that makes things more complex mathematically, my suspicion is that you will find the predictions much more intuitive.